When a new AI capability promises to reveal its hidden inner thoughts, most teams see a magic trick or a debugging superpower. But for engineers building production systems, this moment signals something far more unsettling. Your standard unit tests have just become obsolete. The revelation of internal reasoning chains proves that modern models do not behave like deterministic APIs with fixed inputs and outputs. Instead, they act as probabilistic engines, where the very path taken by logic changes based on hardware constraints, memory bandwidth, or how you phrased a prompt. If your architecture assumes code is static and testable in a linear way, it has a fundamental blind spot: the inner thoughts. Expose that AI inference is non-deterministic by design, driven by dynamic routing mechanisms like mixture of experts, irregular graph structures, or what we are now calling vibe architecting, where prompt phrasing dictates system structure. This means the software engineering paradigm for deterministic logic no longer applies to probabilistic reasoning. You need a new framework for validation and governance if you want your AI systems to be reliable in production rather than just impressive demos. The first step is understanding that these internal thoughts are not abstract software layers, but physical constraints of the hardware they run on. Research into architectures like DeepSeek V3 demonstrates this co-design clearly. This model was trained using 2048 NVIDIA H800 GPUs utilizing FP8 mixed precision formats to maximize efficiency. The ability to route computation dynamically relies heavily on memory bandwidth and interconnect latency across that massive cluster. When the model reveals its inner thoughts during inference, it is often a side effect of the system optimizing for physical efficiency rather than logical consistency. This creates a scenario where non-determinism is not a bug but a feature of scaling logic that cannot be separated from infrastructure limits. The hidden thoughts you see are frequently artifacts of how the hardware handles FP8 trade-offs under load. This means the reasoning path changes based on whether memory pressure forces the system to route computation differently, or if latency spikes cause it to skip certain expert layers in a mixture of experts configuration. You cannot debug this by looking at code alone because the logic is physically coupled to the machine state. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. This hardware logic coupling directly breaks standard testing paradigms used for decades. Unlike traditional deep learning tasks handled by fixed grids, modern models like graph neural networks operate on irregular graph structures where connectivity varies per input. This dynamic routing means the computational path changes based on data topology rather than a fixed matrix multiplication sequence. Consequently, traditional testing methods designed for regular matrices fail to capture the full spectrum of inference behaviors because they cannot predict which specific path through the model will be taken during runtime. When you run a unit test expecting a single output from a deterministic input, you are ignoring that the system might take 5 different paths depending on how data flows through those irregular graphs. The result is tests that pass in isolation but fail catastrophically under real-world traffic patterns where memory access becomes unpredictable. This explains why your validation logic seems to work perfectly in development but breaks when deployed at scale. You are testing for a static world that does not exist in probabilistic inference environments. The situation worsens as we look at the human factor, specifically the rise of what researchers call vibe architecting. AI coding agents like Claude Code or Devon are now making infrastructure decisions without direct human oversight, selecting frameworks and wiring integrations based on prompt wording rather than deliberate design reviews. This creates a phenomenon known as prompt architecture coupling, where the specific phrasing of a request dictates the structural integrity of the system itself. Identical tasks can yield structurally different systems solely based on how they are prompted to an agent. If you ask for a database schema one way, you might get a relational design, ask slightly differently, and you receive a graph-based structure with no explicit warning in your codebase. This makes traditional architectural documentation obsolete unless it captures these implicit choices made by the agents. You cannot rely on static diagrams because the system's architecture is fluid and dependent on how humans interacted with the tool, not just what was requested. To address this chaos, we need new frameworks for governance that treat wisdom separately from intelligence. Current AI-assisted tools often treat unproven guesses as established facts, leading to stale evidence where 25% of decisions become invalid within 2 months due to the speed of generation versus validation. We must adopt a layer that tracks the epistemic status of claims, distinguishing between hypotheses and verified facts before any action is taken. This requires an approach where you tag architectural decisions with their confidence levels or validity windows. If an AI suggests a database schema, treat it as a hypothesis until validated against the system's actual performance constraints rather than deploying it immediately as fact. You must also shift your testing strategy to stop checking if outputs match expected strings and start verifying how the model behaves under varying hardware loads when routing decisions change dynamically via MOE layers. The engineer who understands how these physical limits influence logic will become more valuable than the one who just writes prompts. Your role shifts from coding to architecting for uncertainty, ensuring systems remain robust even when their internal reasoning paths are non-deterministic. In this new landscape, documenting the why not is as critical as documenting what was chosen because you must capture the rejected alternatives and the prompt variations that led to them using architecture decision records designed specifically for probabilistic systems. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.